Hi everyone, this is a talk concerned with searching for dark matter with the Cherenkov telescope array. My name is CSABABALAZS and I'm affiliated with Monash University. So let's get started. The essence of this talk is dark matter, and we know that dark matter exists. It holds our galaxy together gravitationally. Most of matter in the universe is dark matter, about 80%. And we know quite a bit about dark matter. We know the spatial distribution of dark matter within the galaxy or within galaxies similar to ours. And we know that dark matter is mostly found in the center of the galaxy, and its distribution reaches way beyond the visible matter in the galaxy. We also know that dark matter is nearly collisionless, which implies that it's weakly interacting, at least with ordinary matter. And we know that dark matter is stable, and it's cold-ish. So we know quite a bit about dark matter. However, we don't know something very important. We have no idea what dark matter is made of. And this is a really nagging question, especially for particle physicists like myself. The more precise statement is that we have too many ideas, in fact, way too many ideas about what dark matter might be. And the experimental input is just not enough to differentiate between the various assumptions, various possible dark matter candidates. So just to illustrate what I'm talking about, here are a few dark matter candidates which were collected in a physics APS article. And these candidates are special because these are all dark matter candidates which are dark matter particles. And so this doesn't include, for example, primordial black holes or similar dark matter candidates. However, this set is very interesting because what you see here is not just the dark matter particles themselves, but the various theories that these dark matter candidates fit into. From supersymmetry to X dimensions and axions and so on. So there are, I think this shows you that there are really indeed too many dark matter candidates we have to sort out. And the good news is that there are some really interesting dark matter candidates here that we can get handle on them. And I've shaded the ones which I will be concerned with mostly because these actually can annihilate and or decay into typically a pair of photons. And then these photons that are the annihilation product or decay product of these dark matter candidates can be seen producing cosmic gamma rays. These cosmic gamma rays then obviously can be detected by the particular instruments on Earth or in space. So the exciting part is that we are building the Cherenkov telescope array, and I will just call it CTA for short. The Cherenkov telescope array is built on two hemispheres at this point, and previous talks in this and corresponding sessions detail that, so I'm not going into that. I'm a theorist anyway, so I'm interested in the capabilities of the CTA. So amongst those capabilities, a really important one is that this Cherenkov telescope array will be the most sensitive cosmic gamma ray telescope ever built. And this makes it very exciting when we point it toward the right place, in this particular case, toward the center of the galaxy, then we might hope to see a dark matter signal. And so obviously the center of the galaxy contains the most dark matter around here. And then this is one of the main targets for CTA, to search for the possible signal of dark matter. So then after this, there will be some technical content in this talk, which I apologize for those of you who are not particle physicists. However, I wanted to give some insight of how this is done for particle and particle physicists. So here is a colorful picture, which actually shows how the CTA sees the gamma ray background around the galactic center. So the very center of the galaxies is in the middle of this sphere. And then the extent of the sphere is about 6 degrees latitude and longitude away from the galactic center. And all these gamma rays are integrated over all the energies, and then just mapped into intensity. And then the intensity scale can be seen on the right-hand side. So the yellower intensity is the higher one, and obviously the closer one you are to the galactic center, the more intense gamma ray background you see. And then as gradually you get further and further away from the galactic center, the intensity of the gamma ray background diminishes. So we have some idea about how the dark matter is distributed within the galaxy. And as I said before, it's the highest density of dark matter is in the center of the galaxy. And this is if this particular dark matter particle, for example, self-annihilates or decays into photons, then the possible gamma ray signal from that particular dark matter candidate would look something like this. Obviously, in the center or toward the center of the galactic plane, the gamma ray signal intensity is the highest. And then as we get further away from the galactic center, the intensity is going down. So this is the particular signal we are looking for on the top of the background, which I showed you before. Actually, it is really fun to just switch between background and signal and background and signal. A human eye would probably have a hard time to see this particular signal on the top of this particular background. However, a very sensitive telescope coupled with a highly sophisticated likelihood analysis can actually separate the signal from the background. Or can it? So this is one of the questions, and this question can only be answered if we look at the particular spectrum, the energy dependence of the gamma ray counts or gamma ray flux from the center of the galaxy. So what you see here is the spectrum, gamma ray spectrum of the background, or more precisely the various backgrounds around the galactic center. And as you see, the background consists of several things. The leading background is coming from cosmic rays, but there are various other mechanisms to produce gamma ray photons from the center of the galaxy. And these are all taken into account here and then plotted individually. And so the total background would be the sum of these. And as you see, the background is pretty much dominated by these cosmic gamma rays, and its shape is relatively simple. It can almost be described by a simple falling power law. So we also have some idea about the gamma ray spectrum of the signal. And this is what is shown here. And these two images were taken from an archive paper which appeared not long ago. Actually, it's appeared last year in July. So this is the signal from that particular paper, and then this actually shows this has some assumptions. So the key assumption here is that we assume a generic what we call a WIMP, a weakly interacting massive particle, which self-annihilates into various channels, either BB bar quarks or tau plus tau minus leptons, or a pair of W bosons. And then, depending on which annihilation channel is happening, there will be a corresponding gamma ray spectrum, which is shown on this plot. It is also assumed that the mass of the dark matter particle is 2 tera-electron-volt. And the reason for this assumption is that, well, partially because these weakly interacting massive particles tend to have a mass around the weak scale. But the second reason is because it will turn out that the Cherenkov telescope array is most sensitive in this tera-electron-volt mass region for dark matter. So, of course, once we know the signal and the background gamma ray spectrum, then it is much easier to begin isolating them using a specific likelihood analysis. And this type of likelihood analysis have been done in the paper which was published in last year in July by the CTA collaboration. And then this was one of the key results from that paper, which shows us the projected sensitivity of CTA for a generic dark matter particle, generic WIMP. So this plot shows the projected sensitivity of CTA for a generic WIMP, a generic dark matter candidate. And in this case, the assumption is that this candidate is annihilating into a pair of W bosons, and then the colored region shows the projected reach, and above the solid curve in the middle of this colored region, this particular dark matter candidate is observable. There is a horizontal line, a straightish horizontal line, which shows what is called a thermal annihilation cross-section for this particular dark matter candidate. And it's interesting because that's sort of the ballpark where the annihilation cross-section should be based on the amount of dark matter that we observe not just around us, but essentially in the whole observable universe. So what is seen, the main message from this plot is that the CTA excitingly can reach below the thermally averaged annihilation cross-section. So it might be, if this is a really simple dark matter candidate, it might be able to explore a wide mass range, essentially up to 2.5 orders of magnitude of mass range of this particular dark matter candidate, and either find or exclude that. So this is all really nice, and this has been published in a paper by the CTA collaboration last July. However, the interesting thing for this particular talk is that this sensitivity estimate, this particular sensitivity plot does change for a specific WIMP. So it changes WIMP by WIMP, changes from a given dark matter candidate, from one given dark matter candidate to another. And this is because every different dark matter candidate produces various final states, and the dark matter signal from these particular final states is an admixture of final states which are WW, QQ bar, or lepton pair final states. So this particular sensitivity analysis has to be repeated for specific dark matter candidates, and this is what we are doing at this point. So to show you a taste of what is in the is in progress, work in progress, this is the gamma ray spectrum of an inert Higgs doublet, and this inert Higgs doublet is a perfect dark matter candidate. So it produces gamma rays, and the gamma ray spectrum is right in front of you. The approximate background, so this just the background, the energy to the 2.7 power is shown with sort of straightish lines, just to calibrate your eye to the background. And what you can see is that on the right hand side is that for specific masses of this dark matter candidate, this particular signal might be observable. So this is the beginning of the likelihood analysis that one has to go through. At this point, we can just see that this inert Higgs doublet model producing dark matter candidate is a promising one for detection at CTA, and then we have to push through this particular signal and the background which I showed you earlier, a likelihood analysis to see how this particular exclusion curve changes for this model. And so we are in the process of reevaluating the CTA sensitivity for this and several other promising and mainstream models, such as right-handed neutrinos, left-right symmetric models, and various supersymmetric models, for example. So I am going to conclude after the starting brief talk by saying that the CTA will be crucial in the hunt of dark matter, and it will be able to discover or rule out various WIMP candidates, and which ones, and exactly what are the likelihood of discovering and ruling out is in the pipeline, is exactly what we are working on now. As we already know, the CTA sensitivity is highest for 100 GeV to about 1 TeV WIMPs or a couple of TeV WIMPs. And so we are actually looking at specific models which feature these WIMPs, and we are analyzing their discoverability at the CTA. So the most interesting results will be coming out of the experiment over the next decade, which will eventually mean either the end of various dark matter models or candidates, or more optimistically, the CTA might actually find one of these dark matter candidates, which would be a tremendous result. Thank you for your attention, and that's the end of the talk.